Chapter 6, Chemical Equilibrium. Section 6.3, Equilibria that involve pure liquids and solids. When pure liquids and solids are involved in a chemical reaction, their Gibbs energy also depends on the pressure. However, this dependence is often negligible because the molar volume of a liquid or solid is much smaller than that of a gas, are usually 1,000 times smaller. Therefore, we often neglect the pressure dependence of the Gibbs energy for solids and liquids. Now let's look at a pure substance of a fixed amount at a constant temperature. We have dG is equal to VdP. This is just because dt is 0 when the temperature is held constant. And then we have dgm is equal to Vm dP. G sub m is the molar Gibbs energy, V sub m is the molar volume. By looking at this equation, we know the Gibbs energy changes as the pressure changes. And because molar volume is always positive, when pressure goes up, molar Gibbs energy go up. Now let's look at this equation. If we integrate this dgm and Vm dP, we get this equation. The change of the molar Gibbs energy of a substance is the integral of the molar volume of that substance dP. By looking at this equation, we can see if we have a larger molar volume, we have a larger change in molar Gibbs energy. When we have a smaller molar volume, we have a smaller change in molar Gibbs energy. Now let's look at liquids and solids. When we change the pressure, the molar volume of a liquid or solid remains constant, approximately. This is just very hard to change the volume of liquids or solids when you change the pressure. And this is just for the convenience over here. When we integrate this VMdP, we may assume the molar volume of this liquid or solid within this pressure range from P0 to P is roughly a constant. And now we can take this constant out of the integral. We have this equation. Alright, so the Gibbs energy of formation under pressure P minus the standard Gibbs energy of formation is equal to approximately the molar volume of this liquid or solid multiplied by the pressure difference. Again, from here, this integral to here, this simple expression, we assume molar volume is a constant. You can only assume that for a liquid or solid. Do not assume the molar volume is a constant for a gas when pressure changes, because for a gas, when pressure changes, volume changes as well. Again, use this for liquids and solids. And now we're going to evaluate this. We find this is often very small or negligible for solids and liquids. Here's the example. The standard Gibbs energy of formation of liquid water is negative 237 kJ per mole at room temperature. Now let's change the pressure from the standard pressure, which is 1 bar, to 10 bars. So that's a significant pressure change. Now let's look at the change in its Gibbs energy of formation. Now we're going to compute this. The Gibbs energy of formation at 10 bar pressure minus the standard Gibbs energy of formation is equal to the molar volume times the pressure difference. What's the molar volume of water? It's roughly 18 milliliters per mole. And then we have this pressure difference expressed in the unit of pascals. We do the multiplication. I think we will get 16 joule per mole, or 0.016 kilojoule per mole. So now let's look at this number. This is the standard Gibbs energy of formation of water under 1 bar pressure. If we increase the pressure to 10 bars, this number will be changed by how much? By only 0.016, essentially no change. In general, the pressure dependence of Gibbs energy of solids and liquids can be simply neglected. When the pressure of ideal gas increases from 1 bar to 10 bars at room temperature, however, its Gibbs energy changes significantly by 5.7 kilojoule per mole. We can do this calculation assuming ideal gas behavior. When we integrate this molar volume, we change it to RT over P. The reason I use P prime here is because I have the P as the upper limit. Somehow we need to change the notation for the variable. That's it. This P prime is just a dummy variable. You can even replace P prime, this P prime, to beta. I mean, it does not affect the evaluation of this integral. It's gonna be this, and we plug in 10 bars here and 1 bar here. It's gonna be RT ln 10. Plugging R and the room temperature, we get 5.7 kilojoule per mole. So if you change the pressure of a gas from 1 bar to 10 bars, its Gibbs energy will change by this much, 5.7. However, if you do the same pressure change to a liquid, how much does that change? The Gibbs energy changes only by 0.016, and this is 5.7. Huge difference. So if a reaction involves both gases and condensed phases, over here a condensed phase can be a liquid or a solid. So if we have gases, liquids, and solids, then we will simply assume the Gibbs energy of formation of the liquids and solids are just independent of pressure. There's no change to the Gibbs energy of formation to the liquids and solids. You simply look up the standard Gibbs energy of formation for the liquid and solid and use those values, no matter what the pressure is, only because their pressure dependence is negligible. Again, the root reason is the molar volume of liquids or solids are so small. It's much smaller than the molar volume of a gas. Under typical experimental conditions around room temperature and 1 bar pressure, the ratio between the molar volume of a liquid or solid and the molar volume of a gas is in the order of 10 to the power of -3, or you can say just they differ roughly by a factor of 1000. Well, it could be 1000, 2000, 800. Just this is just the order of magnitude. Still, you can see, this number is much larger than this number, roughly in the order of 1000. When a reaction involves only liquids and gases, I'm sorry, over here there's a typo. When a reaction involves only liquids and solids, I'm sorry, we need to replace this with solids. The Gibbs energy of reaction may be considered independent of pressure unless the pressure change is tremendous. For example, several thousand bars. Over here, if the pressure change is 1000 bar, a volume difference of 1 milliliter results in only 0.1 kilojoule difference between the Gibbs energy change. Here's a simple illustration. If you have 1000 bars and then there's a volume difference of 1 milliliter, we do the calculation. We convert bar to pascals. We convert milliliter to cubic meter. Pascal and cubic meter are SI units. So in the end, we get just 100 joule, which is only 0.1 kilojoule. It's still much smaller than this number. And right here, when we do this calculation, we assume the pressure change for this condensed phase is 1000 bars. Over here, it's only 10 bar for the gas. Okay, only 10 bar pressure change for the ideal gas. What if the pressure change is 10,000 bars? Then the volume difference of 1 milliliter may result in just 1 kilojoule difference between the Gibbs energy change. Alright, so we are comparing a pressure of 1 bar and a pressure of 10,000 bars. So if in this reaction there is volume change of 1 milliliter between reactants and products, and then this pressure change will cause some Gibbs energy change of the reaction, but not much. It's only 1 kilojoule. Here's a numerical example problem 6.3.1. So over here, the Gibbs energy of fusion of water is 0 at 0 degrees Celsius and 1 atm. Now we're going to change the pressure to 100 atm, and we're going to compute this Gibbs energy of fusion again at the same temperature, 0 degrees Celsius. We're given the density of ice, we're given the density of liquid water at 0 degrees Celsius. They are 0.917 and 0.9997. The liquid water has a higher density and therefore smaller molar volume. So during this fusion process, the molar volume will change. Now let's look at this fusion process. It's going from solid to liquid. We can just assume this solid ice is our reactant. This liquid water is the product. So we're going to treat this fusion process as if it were a reaction. The molar volume of ice and water are 18 and 19.6 milliliter per mole given this density values. It's mostly just the density, 18 grams per milliliter divided by this, we'll get the molar volume 19.6. 18 grams per mole divided by this density, we'll get 18.0 milliliter per mole. Alright, let's just look at the Gibbs energy of this reaction. It should be the Gibbs energy of formation of the products minus the Gibbs energy of reaction, Gibbs energy of formation of the reactants. So really it's just liquid water minus ice. And now this time, since we are using a different pressure, 100 atm, we're going to take that into account. So we're going to look at the Gibbs energy of formation of liquid water over here. It's the standard Gibbs energy of formation plus some correction. We're using molar volume times the pressure difference for liquid. And now this is ice, so we have the standard Gibbs energy of formation and the molar volume of ice times the pressure difference. The reason we can do this is because we're assuming the molar volume of a solid and the molar volume of a liquid do not really depend much on the pressure. Although we're changing the pressure from 1 atm to 100 atm, the molar volume is still roughly this and this. They are roughly constant. That's why. And now we can combine this term and this term. We will get the standard Gibbs energy of reaction for this fusion. And also we'll have this molar volume of liquid minus the molar volume of ice over here times P minus P naught. P minus P naught is roughly 100 atm. And now we need to look at the molar volume change. It's small, it's roughly 1.6 milliliter per mole. So we plug in all the numbers, we get negative 16 joule per mole, and we get negative 0.016 kilojoule per mole. So even if we change the pressure from 1 atm to 100 atm, the Gibbs energy of this fusion process changes only by negative 0.016 kilojoule per mole. However small, it's still a negative number. That means, well, in this case, the product side is going to be slightly favored. The liquid phase is going to be slightly favored when this is negative. The reaction should proceed to the right hand side. What does that mean? That means if you exert a really high pressure, you may convert ice to liquid water. And now we're going to just watch a video. We're going to exert a really high pressure to ice at 0 degrees Celsius. It's going to melt the ice. So this is a YouTube video. For copyright issues, I can only
I'm going to try to demonstrate something called
bit.
regelation, which is where you provide a pressure onto ice and that turns it into water. But after that pressure is removed, it freezes again. So
over here, there's a wire. It's actually a string from a guitar. And we have some heavy objects here. And you can imagine how much the pressure is because the area is so small. And we have 2 bottles of water, so tens of newtons divided by a very small area. And you can see this wire, this guitar string is cutting the ice. So really it's not really cutting the ice, it's cutting liquid water. Because of the pressure, the ice actually has melted and the string is just cutting through this liquid water. So in the end, I think we're just cut through the whole thing.
You can compress the ice, turn it into water, and then when that
Alright, again, I can't play more than, I don't know, maybe 20 seconds. So over here, You can just search does pressure melt ice. You can search for this video. Now let's move on to the next slide. Again, I was just pretending this is a chemical reaction, so we can define the Gibbs energy of reaction for the fusion process from solid to liquid. All right, and then we have this equation. We have the Gibbs energy of reaction is equal to the standard Gibbs energy of reaction plus some correction. This correction is due to the pressure change from 1 atm to 100 atm, and this is important only because the molar volume of ice and the molar volume of liquid water are different. Well, what if they are exactly the same? Then, well, there's no pressure dependence at all. So if these two are the same, you get just 0 times the pressure change, and then this part just disappears. Alright, I'm gonna move on to slide 10 over here. Here's another example, problem 6.3.2. Under what pressure will graphite be converted to diamond? Well, this can be done with a huge pressure. However, this is going to be extremely slow. Alright, but still, theoretically, let's look at this. When will this graphite be converted to diamond? They're both carbon. So when the Gibbs energy of diamond is lower than the Gibbs energy of graphite, and then this conversion will happen under the given temperature and pressure. Now let's look at the density of graphite, the density of diamond, 2.26 for graphite, 3.51 for diamond. From these two numbers, you know the molar volume of the diamond is smaller than the molar volume of graphite, and we can compute the molar volume easily. It's just 12 grams per mole divided by 2.26, 12 gram per mole divided by 3.51. We get the molar volumes of graphite and diamond. They are 5.3 milliliter per mole and 3.4 milliliter per mole. And now we have the standard Gibbs energy of formation of graphite and diamond. They're 0 and 2.9. Look, graphite has a lower Gibbs energy of formation. That means graphite is favored at room temperature and 1 bar condition. This is 1 bar condition. However, for this graphite to diamond conversion, we can make it happen if we have high enough pressure. So now let's make it happen. Let's look at this reaction from graphite to diamond. The Gibbs energy of reaction is again the standard Gibbs energy of reaction plus the molar volume of the product minus the molar volume of reactant, which is graphite, and then multiplied by the pressure difference. We can plug in all the numbers. Okay, 2.9 kilojoule per mole over here. This is the standard Gibbs energy of reaction. It's just diamond minus graphite. It's a positive number, 2.9, and we have the molar volume of diamond, molar volume of graphite. We put in the units and then times P minus P naught. So when does this happen? This happens only when delta G of R is less than 0. The reaction moves forward spontaneously. So I'm going to say when this whole thing is less than 0, or the Gibbs energy of this reaction is less than 0. Either way is correct, but now I'm going to use this inequality. I'm going to say this is less than 0, and this can be converted to P minus P naught should be greater than 2.9 kilojoule per mole over 1.9 milliliter per mole. How do we do this? Division. We need to use SI units. Mole and mole cancel, kilojoule becomes joule, and milliliter becomes cubic meter. We do the calculation, we get 1.5 billion pascals, which is 15,000 bars. It's a very high pressure. So if you really want to convert graphite to diamond, at least you need 15,000 bar pressure to make this reaction favorable thermodynamically. So again, diamond can be thermodynamically favored at room temperature, but it has to be very high pressure. How high? At least 15,000 bars. And note that a moderate change in pressure, for example 5 bars, will do nothing to the graphite or diamond. Virtually nothing.